Hello there. During this session I'm going to be talking about analog and digital signals. I'm going to be doing a comparison and also looking closely at how we can convert from analog to digital, and within that I'm going to explain about the binary number system. Which brings on to the t-shirt. There are only 10 types of people in the world, those who understand binary and those that don't. Hopefully by the end of this session you're going to understand that joke. And hopefully a little bit more than that with any luck. So let's start off by thinking about digital and analog. So what is the difference between a digital signal and an analog signal? Well, digital signals can only be in one of two states, okay? Whilst analog signals are continuously changing variable. So it's best shown graphically. Here we have digital signals, two states, 0 and 1 is the norm, but we're saying is that there's going to be very clear distinguished states. Whilst an analog signal, they're continuously changing variable. So that means that every single number available can be taken up potentially. So that's digital and analog. As we see it, let me just get you to think about digital devices and analog devices. So a digital device will have very clear fixed numbers which you can display, whilst an analog signal will show a continuous scale. So we've got two voltmeters. The one on the left hand side is an analog voltmeter, and on the right hand side we have a digital voltmeter. Two examples from a car. We have a speedometer, and this shows the continuous speed scale, so that is an analog, and we also have a fuel gauge, and again that is an analog. Now it's interesting here, the voltmeter we've got 2.52. Okay. What we're saying here is that it's showing a very clear distinct number. Yes, there's 2.53 and 2.54, but we're not showing any of those numbers potentially in between, so therefore it is a digital device and not an analog device. Let's talk about binary numbers, okay? So binary numbers are the tool for digital devices. The binary number system, or the base 2 numeral system, represents all values using just two symbols, typically 0 and 1. Okay. Now what we have here is that each position in the number increases to a base 2. Okay, so let me show you how this works. Okay. So I've got 0, which is 0, 0, 0. I'm going to use 4 numbers to show just to help me show, but I could start off with 0 equals 0, and then 1 equals 1. Now then the next problem I've got is, okay, I've got 1 but I don't have 2 available to me, so how am I going to show 2? Well, that means I have to show this as the next base, so that means I'm going to show 1 and then 0, so that means that there's 1 number which is 2 to the power 1, and then 0 additional ones. This kind of makes sense. And then I say 3 is just going to be the value I'm showing for 2, which is 0, 0, 1, 0, plus then I'm going to have an additional 1. Okay. Again, now get into a situation where, okay, I've got 3 shown, but to get to a 4, well, that means I'm going to have to go up to increase the base. Okay, so that means I'm going to increase 1 step along, and in each situation, so this is the 3rd number along, 2, 3, and that represents the number 4. Okay, and then I keep on going through this process, adding 1 number at a time. Let me show how this works out just with some examples, which hopefully will make it clearer. So, to convert from binary to decimal, you must identify the value related to the position of 1 and add. So what we have here, the number 60. Okay. The 60 is actually the sum of 32, 16, 8, 4, no 2s and no 1s, and that adds up to 60. Now 66, as it happens, the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th base gets the 2 to the power of 7, takes me to 64. So what I've got here is 64 and then I need an additional 2 to get to 66, so it becomes 100010 is 66 in binary. And that's the secret with all of these examples I've got here. What we can see is that all we're doing really is we're working out the value of each one. So depending on its location, it has a different value, and then we're going to add those up. So if we look at 165, we've got, starting from the smallest number, we've got a 1, so that's going to equal to 1. 0, which doesn't equal to anything, and then another 1, that's equal to a 4, so I'm adding those numbers up. 0, 0, the next 1 is equal to 32, and then 0, and the next 1 is equal to 128. If I add up those numbers, I'm going to get to 165. Now, for those people doing IB physics, don't worry, you're never going to have to handle a number above 5 binary bases. So that's how binary numbers work. It's a way of giving us all numbers, but only using 2 numbers to show it. The IB asks us to make sure we're aware of the term, the least significant bit and the most significant bit. I'll talk about what a bit is in a moment. But if we have a binary representation of 149, the LSB, or the least significant bit, is represented by the smallest 1. Whilst the binary representation for 149, the most significant bit, is represented by the value of 128. So that was the value I have here. Okay, so that's the most significant bit. So that's the largest one. So the most significant bits, least significant bits. Let's just think about what this idea of bits and bytes. So a bit and a byte. We know that everything's made up of a 1 or a 0, and this is known as a bit. Okay. A byte is a string of 1s and 0s. Now above we're showing an 8-bit byte. Okay, so a byte is a string of bits, and it can actually represent 2 to the 8, so it can represent 256 numbers. So those 8 zeros and 1s could represent 256 numbers. And at the bottom there I've got a couple of examples. I've got a 1 byte, which is an 8-bit byte, and then I've got a word which is 16 bits, and that's created from 2 bytes. So we've got to recognize that when I said there's 8 bits could equal 256 numbers, I know this because if I put every value as a value of 1 and add them all up, it gives me the number of 256, which is the highest number possible. A quick note, in the decimal system, kilo means 1,000. So in the binary system, kilo actually means 1024. This is because 1024 is 2 to the 10th power, or the maximum number that can be represented by 10 bits. So there's 10 ones in a row can represent the decimal number 1023 plus the value that we're set to, so to 0, so that equals 1024 possible numbers. So just a quick note, this means that a computer may be described as having 640 kilobytes of memory when really it's 640 times 1024, which is 655,360 bytes in total. Okay, so just to mention that. So binary is how we show digital values. Now, often we need to sample, we need to transfer from analog to digital. And we do this because, or we do this by going through these first steps. First of all, a set of relative sample gaps. Okay, so this is about the sampling. We're going to find out what the amplitude is. Now, this amplitude is then going to be rounded to an integer, so that's kind of known as quantizing, and this is then going to be changed from what's known as an analog to digital conversion. So now I've got all these values as integers, and as integers I can then change them into a digital signal. This is encoding. At the other end, in this case my digital values are shown as 3 bits in this example, but it could be any number depending what information you're trying to transfer. This digital signal is transferred, and at the other end it is decoded. So the binary signal is sent and then decoded by a DAC, a digital to analog converter, to give a new analog signal, and that analog signal can then be sent out or listened to. So that's how we can convert from digital to analog, or analog to digital, or vice versa. So that is my quick introduction to digital and analog signals.